Hello, welcome back to Math 104. So for today's class, we're actually going to continue discussing U-substitutions and other factoring techniques. We want to begin with where we left off, which was our conversation on how to use U-substitution when factoring polynomials. This is especially helpful when you have more complex trinomials where you have to kind of change that polynomial that you were seeing so that it becomes familiar, like something that you're used to factoring. So we're going to take a look at some extra problems just to make sure that we understand exactly how to use U-substitution when factoring. Let's take a look. So for part C, we have 5 times x plus 1 squared minus 13 times x plus 1, and then minus 6. Hi, Keith. Thank you so much for saying hello and stopping in. It's great to see you. So in order to use this U-substitution idea, we really, like for me, as I was learning this, I always wanted to look at, what I noticed was in common between my terms, the first and the second. So notice here I have an x plus 1, and that's a squared factor, and then I have just an x plus 1. So immediately my mind thinks, okay, well, if I called u x plus 1, then that means my first term, meaning if I take that u and I square it, I would account for that x plus 1 squared piece. So now that I've decided what I'm going to call u and recognize that u squared is simply the x plus 1 squared, I can make my substitution. So this becomes 5u squared minus 13u minus 6. By replacing the x plus 1 with u, making that u substitution, I now have a polynomial that I'm actually really familiar with. I know that because I have a trinomial where my leading coefficient is greater than 1, I'm going to choose to use AC grouping method. So I'm going to go ahead and write that down because I find that to be incredibly helpful. AC grouping method. We go through the same concept that we were going through before. A times C, that's 5 times negative 6, right? A is 5, B is negative 13, C is negative 6. So 5 times negative 6 is negative 30. My goal is to find factors of negative 30 that combine to give me a negative 13. So back when we were working through this in 098, we would actually list all of those factors. If you want, you can still do that. You can still write 1 times 30, 2 times 15, 3 times 10, 5 times 6, and you can figure out which combination of factors will give you a negative 13. Consider that your signs must be different. One has to be positive, one has to be negative when you multiply in order to get negative 30. So right away in my mind, I see that 15 times 2 gives us 30. But more specifically, I have to place the sign so that when I combine these two, I get a negative 13. Well, in order for that to happen, the larger number must be negative. So let's double check. Negative 15 times 2 is negative 30. Perfect. Negative 15 plus 2 is negative 13. Beautiful. Now that I have my two factors of AC that combine to give me B, I can go through the process of grouping, right? We learned that in order to group, we must have 4 terms. This implies we're going to replace our B term, this negative 13u, with the two factors that we found here. So I'm going to rewrite this as 5u squared minus 15u plus 2u minus 6. So here we are, we have our 4 terms which we can now factor by grouping. So this is the part that we find goes super, super quick. I'm noticing in this class that you're all really taking to this style quite easily, which is really, really nice. Notice that for each group, I'm simply factoring out the GCF. And then I also notice that because I have a common factor of u minus 3 in each of these two terms, I'm actually going to factor the u minus 3 out, and I'm left with 5u plus 2. Now, as we discussed before, remember, I made a substitution. I called u x plus 1. But I cannot just say my answer is u minus 3 times 5u plus 2. I've got to put it back. So having said that, I'm going to note that u is x plus 1. So I'm literally going to replace u here with x plus 1. But don't forget, there's a minus 3. Interesting, right? This is kind of neat. This is an alternative method to writing x plus 1 squared out twice, distributing, multiplying by 5, and then distributing the negative 13, and then finding, just too much. Ooh, gross. So instead, this is why we use that U-substitution, to save us lots and lots and lots of time. So I replaced u with x plus 1 in our first set of parentheses. I must do the same in our second set of parentheses. Remember, there's a coefficient of 5, so it's going to be helpful to use parentheses around that substitution. Noticing that I have x plus 1 minus 3, if you ever saw that, you would simplify. I know you would. You would say, oh, wait a second. X plus 1 minus 3, that's just x minus 2. And then if you saw 5 times x plus 1 plus 2, you would say, oh, let me just distribute this 5. That gives me 5x plus 5 plus 2. And then you would say, I'm almost done. Not quite. I have like terms. Let's put them together. So I get x minus 2 times 5x plus 7. And that is your final factored form. Using the U-substitution, we save so much time. One of these days, I will take this problem and I'll expand it for you and show you just how much lengthier this problem would be. Okay? Save yourself the time whenever possible. The cool thing about part D is it's the exact same process. So notice again, we have 4x plus 5, that's a squared quantity. And then we have 4x plus 5, and this is your singular quantity, right? So immediately my eye goes to, okay, well, what if I call this one u? Then that means this one's u squared. Perfect. That's exactly what we're looking for. So we're going to call u 4x plus 5. And if you square both sides, you notice that u squared is 4x plus 5 quantity squared. Having this representation allows us to make a substitution and to factor. So it's very similar to what we just saw in part C. So we have 3u squared minus 2u minus 1. Notice it's a trinomial. My leading coefficient is greater than 1, so I'm going to use AC grouping. Same idea, AC grouping method. And note that we are going to start by multiplying by a times c. So 3 times the negative 1 gives us negative 3. And we want factors of negative 3 that combine to give us a negative 2. We know that we only have one set of factors, 3 times 1. But when we combine, we need a negative 2. So our larger term must be negative and the smaller must be positive. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. Let's go ahead and sub out our b term and replace it with the 2 factors so that we have 4 terms. So we have 3u squared, there's our first term, minus 3u plus 1u. These are the 2 terms that replace our middle term, our b term. And then minus 1, so you bring down the last one. So we went from a trinomial to a 4-term polynomial. Also note that these are exactly the same expressions. We just expanded the second one, right? So we have negative 3u plus 1u is in fact negative 2u. So these are the same polynomial. Next, we can factor by grouping. Go through the same process. Our GCF here is 3u. That leaves us with u minus 1. Our GCF here is a positive 1. That leaves us with u minus 1. And then, of course, notice that we have the exact same binomial in each set of, in each term. So we are going to factor out that u minus 1. And we're left with 3u plus 1. Because we made a u substitution, we now have to plug that right back. So u was 4x plus 5. I'm going to go ahead and rewrite this. So if u is 4x plus 5, that becomes 4x plus 5 minus 1. There's the first set of parentheses. And now let's substitute 4x plus 5 in for u in our second set. So we have 3 times 4x plus 5, and then plus 1. Reasonably speaking, you always want to combine like terms whenever you can. So we have 4x plus 5 minus 1. That leaves me with 4x plus 4. We're going to distribute. That gives us 12x plus 15 plus 1. I'm actually going to, well, I'll rewrite both. Why not? So we have 4x plus 4, and then we have 12x plus 16. Now remember what the name of the game is here, and that is to factor completely. Especially for problems like this, I want you to remember that you're not factoring part of the way. You've never seen instructions that say factor as far as you want, right? You've never seen that. Anytime you actually apply these ideas, you want to complete it. You want to literally complete it. So it really should go without saying factor completely. You should just say factor. So what that means is you have to look at your factored form and see if you can go further. If you can, you should. So let's take a look. It's kind of like fractions, right? If you reduce, you want to reduce all the way. You don't want to just like reduce half of the way. That's weird. Let's take a look. Notice in your first set of parentheses, you have a 4x plus 4. Immediately, my eye is drawn to the fact that I have a common 4. So I'm going to factor that out. If I factor 4 from each of the terms, I'm left with x plus 1. Next, I'm looking at my second set of parentheses and I say, oh, wait a second. I can also take out a 4 here, right? If I factor out a 4 here, that leaves me with 3x plus 4. Now, if you're wondering how you write your answer, now that you've factored out a 4 from each set of parentheses, well, I urge you to remember what this is actually saying. If I were to read this from left to right, it says 4 times x plus 1 times 4 times 3x plus 4. Well, so it's just a product of factors. And in which case, if you have a 4 here and you have a 4 here, well, what's 4 times 4? 16. So your final answer should be 16 times x plus 1 times 3x plus 4. There's your answer, completely organized and put together. Hopefully that made sense. Our next problem is definitely a little bit trickier. You probably look at this and you're thinking, whoa, what would I do here? Well, again, I urge you to consider what you see in common, what you're seeing more than once. So for instance, with part C, I noticed x plus 1, x plus 1. With part D, I noticed 4x plus 5, 4x plus 5. Well, with part E, I'm noticing a minus b, a minus b. It's just in a slightly different format. Let's try it out. What's the worst that can happen? I'd have to erase and start again. What if I call u a minus b? Just like that. Let's see what we end up with. Okay, so a minus b is u. And then here I have a minus b again, which is u. Then we have a minus 1. So u minus 1. And then I have minus 20. Well, naturally, I'm not looking at a trinomial, right? I'm looking at a binomial. But naturally, I would say, well, maybe I should distribute and see what I get. Okay, so I'm going to distribute. And this gives me u squared minus 1u minus 20. Aha! Now I have a trinomial. Leading coefficient is equal to 1. Okay, cool. Let's try to use trial and error. I like to use trial and error when my leading coefficient is equal to 1. I use AC grouping when my leading coefficient is greater than 1. So with trial and error, I need to find factors of negative 20 that combine to give me a negative 1. Okay, 1 times 20, 2 times 10, 4 times 5. Aha. Okay, so we've got 4 times 5. Keep in mind that when we multiply, we want a negative 20, and when we combine, we want a negative 1. So the larger number must have that negative. Positive 4 times a negative 5 is a negative 20. 4 minus 5, negative 1. Check. So now I can go ahead and write my factored form. We learned this when we were discussing trial and error. So u squared breaks down into u times u. And then we have our factors, positive 4 and negative 5. That's what gives us a negative 20. So plus 4 minus 5. Just to make sure we're on the right track, u squared minus 5u plus 4u. That gives us a negative 1u. And then minus 20. That's perfection. The last thing we have to do is sub u back in. So we called a minus b u. Let's put it back. U is a minus b, so my first factor is a minus b plus 4. And then again, u is a minus b, so let's replace it. A minus b minus 5, and there is your answer. Okay, hopefully that made a lot of sense. Look for things you see in common and just give it a shot, see what happens. The worst that can happen is you hit a roadblock and you decide, you know what, this is not going well, and let me just start again from scratch. Remember, the big piece here is look for what you see repeating itself, you know. Take a look and see if you can identify, you know, the pieces that are appearing more than once, okay? Cool. Let's go ahead and turn the page. We're now ready to discuss the difference of two squares. This is going to start off kind of as like a repeat of what we've seen in Math 098. Don't be alarmed. Obviously, this is going to get a little bit more extensive, but just in the meantime, let's start off nice and easy, even though it is a review. So first off, as a reminder, we have a plus b times a minus b. So I wanted you all to multiply this, right? So we're going to distribute the a, then we're going to distribute the b. So if we multiply, we get a times a, which is a squared, a times negative b, which is negative ab, b times a, which is positive ab, and b times negative b, which is negative b squared. Notice that your inner terms completely cancel. So this leaves you with a squared minus b squared. What this is showing you is that if you were to factor a squared minus b squared, well, your factored form would look like this. So the general form is a plus b times a minus b. I have that here as your general rule in case you ever wanted to look at that again. Another way to note if you have perfect squares, which will allow you to factor in this form, is try to take the square root of each term. If you can, then they are perfect squares. Keep in mind, though, this is called the difference of two squares. You cannot factor in this way if you have this sum of two squares. You cannot factor in this format. If you had the sum of two squares, we're looking at the complex number system. Okay, let's take a look. Notice, factor the following difference of squares, make a U-substitution if necessary. Hint, hint. Luckily for us, part A is very, very tame. We have x squared minus 9. Notice that we have subtraction, difference. X squared, that's a perfect square, right? Because x times x is x squared. 9, that's a perfect square because 3 times 3 is 9. So when we go ahead and factor, keep in mind the form a plus b, a minus b. So we essentially break each of these terms down. That becomes x plus 3, x minus 3. The difference of two squares. Simple. Let's do it again. 16x squared minus 25y squared. Let's look at each term. 16x squared. I know that 4x times 4x gives me 16x squared. I know that 5y times 5y gives me 25y squared. That means this is in fact the difference of two squares. So let's go ahead and factor. We know it's going to be a plus b, a minus b. So when we break this down, we have 4x plus, and then break this one down, 5y, and then we have 4x minus 5y. And that's your factored form. Very nice. Let's continue with this idea by checking out part C. Part C reads 3x to the 6th minus 75y squared. Well, wait a second. X to the 6th is a perfect square, but 3 isn't. One of the biggest things that I never want you to forget, please don't ever forget this, is step number 1 of factoring, and that is GCF. Please make sure you factor out the greatest common factor first from all terms, no matter what. Take a look. So I'm going to factor out my GCF, which is actually 3. So let's factor 3 out. That leaves me with x to the 6th minus 25y squared. Like we discussed in class, I'm going to go ahead and hold on to that 3. Just set it aside. It's a little distracting, but I'm not going to forget it because I'm physically holding on to it. Next, inside the set of parentheses, I have x to the 6th, perfect square, and I have 25y squared. We already know that's a perfect square because we did that in part B. So this is, in fact, the difference of 2 squares. Cool. Let's go ahead and factor it then. When we break down x to the 6th, we get x to the 3rd times x to the 3rd. Remember the product rule. Keep the base, add the powers. X to the 3rd times x to the 3rd is x to the 6th because you have to add the powers. We have plus and we have minus. And then, of course, we know that 25y squared breaks down into 5y times 5y. Another way to think about this is if you broke negative 25y squared down evenly, you would essentially say, oh, well, I'm going to have a positive 5y times a negative 5y if I ever wanted to have a negative 25y squared. Beautiful. I'm going to lift up my finger. I have a 3 as my GCF. I'm going to bring that right down, and there is my final answer. There is my factored form. Cool. Take a look at part D. We have x plus 5 quantity squared minus 36. I don't know about you, but it looks similar to what I'm used to, but not quite. So I would actually use a U-substitution in this case. The piece that's throwing me off is that x plus 5. So what if I said, let's call you x plus 5. If I replace x plus 5 with u, then I have u squared minus 36. Well, I know how to factor that. That represents the difference of 2 perfect squares. Okay, so let's go ahead and write out our parentheses. U squared breaks down into u times u. Negative 36 breaks down into positive 6 times negative 6. So far, so great. U squared minus 6u plus 6u, those cancel, minus 36. I love it. And now all I have to do is put that back. So that leaves us with x plus 5 plus 6, and then x plus 5 minus 6. And you would most certainly combine like terms. You're not just going to leave your answer like this. If you looked at this, if you looked at somebody else's paper and they had this written down, you would say, hey, that's 11. And that's a negative 1. You would fix it, right? You'd combine like terms. So your final answer is x plus 11 times x minus 1. And there you have it. That is a great question in terms of when should you use a U-substitution. When I saw this kind of expression, my mind went straight to, if I don't use a U-substitution, I'm going to have to expand this out and then do all the math before I can even factor. And that to me kind of sounds like a really big hassle, especially when I know that if I just take this expression and call it u and then rewrite it, I can factor this all day long. I become super comfortable factoring something like this. This is a difference of 2 squares. And once I have factored in the simpler form, I can then replace the u with the x plus 5 and then simplify. James, let me show you again. Take a look at part E. We have 5x minus 8 to the second power minus 81. Isn't this a perfect example to say, well, I don't want to write 5x minus 8 twice, distribute, combine like terms, bring the negative 81 in there, and then factor, if really I could just say, make u 5x minus 8, right? So check this out. If I say, let's call 5x minus 8 u, then this becomes u squared minus 81. Now we're looking at a binomial that we're familiar with. We're looking at a binomial that we factored so many times already before. We know this is definitely the difference of two perfect squares. So we're going to go ahead and factor this. U squared breaks down into u times u. And then negative 81 breaks down into positive 9 times negative 9. Once we actually factored our polynomial containing u, let's throw that 5x minus 8, let's substitute it right back into each set of parentheses. So I'm just going to bring this over here so I could see this a little easier. This gives me 5x minus 8 plus 9 and 5x minus 8 minus 9. And then I just have to clean up, combine like terms. Negative 8 plus 9 is a positive 1, so it's 5x plus 1. Negative 8 and a negative 9 is a negative 17, so 5x minus 17. And that is your final factored form. U-substitutions can be incredibly helpful. James, that's a great question. In terms of your GCF, the U-substitution is not replaced so that it becomes the GCF. What we end up doing with that U is we replace some sort of expression, right? And then it becomes a form that is easier for us to factor. It takes away from having to, for instance, in our previous problems, it takes away from having to distribute, open up the polynomial, combine like terms, and then factor. By using that u to replace that expression, we can then actually factor because it's in a form that we're used to, that we're familiar with. It's not a GCF. I want you to notice, let me go back to the notes, I want you to notice that u squared minus 81, there was no GCF. Right? If there were a GCF, we could have factored it out of both terms. Take a look at part C. I did have a GCF. I divided 3 out of each term, right? That's what it looks like when we factor out that GCF. But in this case, I'm looking at this with fresh eyes. This is a binomial that is in fact the difference of two squares. So that's what lets me apply the formula. The formula for the difference of two squares is as follows. If you have a squared minus b squared, it gets factored as a minus b, a plus b, or vice versa, a plus b times a minus b. Okay? And that's essentially the moral of the story. It is just sometimes when we have complex polynomials like this, we can replace that expression with u and then factor and then sub back in. Okay, hopefully that was helpful. And again, with practice, this definitely becomes a lot easier. I think one of the biggest things is being comfortable with factoring in its general form. So are you comfortable with factoring the difference of two squares? If I gave you any, standard non-complex, not these challenging types of problems, but more like basic stuff. If I gave you those polynomials, those binomials, could you factor using the difference of two squares? If you feel very confident about that, then take the next step. Look at these more challenging problems and say, okay, well, if I can manipulate them so that it looks like the basic ones, like the ones I'm used to, can I factor now? And then make that substitution and then simplify. okay? It is going to take a little bit of practice, but you're going to be just fine. I have a note here on the side that says, can x squared plus 9 be factored? And no, this cannot. This is not the difference of two squares. So no, this cannot be factored using real numbers. Okay, just keep that in mind. So if you have the sum of two squares, you're not going to actually factor using real numbers. Okay, perfect. We'll actually learn more about this later in this exact class. We do talk about complex numbers later on. Beautiful. We're now ready to talk about factoring perfect square trinomials. This is something you may or may not have discussed in your last class. I find it helpful if you can identify perfect square trinomials. So we already know what perfect squares are, right? 1, 4, 9, 16, 25, 36, 49. Those are all perfect squares. X squared, x to the 4th, x to the 6th, x to the 8th, etc. So we know how to identify perfect squares. What's different is what it looks like when you are factoring a perfect square trinomial. So what I'm going to do with you is we're going to factor these perfect square trinomials, and what we'll do is we'll factor based on our knowledge of using trial and error, and then we'll do a mental check to see if we were accurate. Take a look. For part A, we have x squared minus 10x plus 25. So we already know that this is a perfect square trinomial set of problems. Okay, notice your first term, perfect square. Notice your last term, perfect square. Interesting, right? Now what I want us to consider is if we were using trial and error, you would say, okay, well, I need to find factors of positive 25 that combine to give me negative 10. And you would say, well, I know 5 times 5 gives me 25, but if I want to combine them, I need a negative 10, so that means they both must be negative. Negative 5 times negative 5 is positive 25. Negative 5 plus negative 5 is negative 10. So if we were just using trial and error, I would say, okay, well, x squared breaks down into x and x, and then we have our two factors, negative 5 and negative 5, which we input inside the set of parentheses. Let's double check. X times x, x squared. Negative 5x and another negative 5x give us negative 10x. Check. Negative 5 times negative 5, positive 25. We have just answered this correctly. We have just factored correctly. I do want to point out that if your answer is x minus 5 times x minus 5, so there are actually two factors of x minus 5, you can get fancy with it. So I'm going to say or, meaning you could also write your answer as x minus 5 quantity squared. These two are exactly the same expression. So if you wanted to write your answer as the square of the x minus 5, that's perfect as well. Not bad, right? So we're going to do it again, and we're going to explore, is this a perfect square trinomial? Okay, we have x squared, so that's definitely a perfect square. We have 36, that's definitely a perfect square, because 6 times 6, right? And wait a second. If 6 times 6 is 36, well, 6 plus 6 is 12. Okay, let's factor. This becomes x plus 6 times x plus 6. Always double check. X squared. 6x plus 6x is 12x plus 36. And there's your final answer. Not bad, right? I think perfect square trinomials are actually pretty cool because of this fact that you're able to kind of, look at the fact that we have perfect squares and we break it down similar to how we broke down our binomials. So again, just so that you have it, you could rewrite this as x plus 6 quantity squared. Okay, cool. Take a look at part C. the first thing my mind does is it says, do I have a GCF? I have a 4, I have a 28, I have a 49. Nope, I do not have a GCF that I can factor out of all three terms. So that's not happening. We look at the x's. If the last term had an x, then we would factor that out. But it does not. So the next thing I notice is I have a trinomial, and I say, wait a second, 4x squared, that's a perfect square. I know that 2x times 2x gives us 4x squared. 49, that's also a perfect square. I know that 7 times 7 gives us 49. Now, I want you to notice in the previous problem, when our C term was positive, that meant that our factors had to have the same sign. Now, because my B term was a negative 10, that indicated my signs both had to be negative. Check out part B. Notice my 36 is positive, my B term is positive, so both terms have to have the positive sign. Let's look at part C. In order to get 49, my signs, a positive 49, my signs have to be the same. Well, the B term tells us they both have to be negative. So I'm going to go ahead and start writing my factored form. I know that both of my signs must be negative. When we break down 4x squared, since it's a perfect square, we say, oh, that's 2x times 2x. And when we break down 49, we say, well, that's just 7 times 7, right? Let's double check. 2x times 2x is 4x squared. Minus 14x minus 14x, that's a negative 28x. And then positive 49. Perfect. That concludes your factoring experience for part C. We're going to continue with this idea just to make sure that we're driving this home. I highly recommend that if you are watching this video at a later date, I would say pause here and then work through the next set of problems to see if you can get through parts D through G as smoothly as possible. Okay, I would say definitely pause it and see how the rest go. But let's continue together. So we have 16x squared plus 24x plus 9. Perfect square, perfect square. And I skipped the first step GCF only because in my mind I noticed there is no GCF. So let's go ahead and write our factored form. 16x squared breaks down into 4x and 4x. 9 breaks down into 3 and 3. Notice the signs are going to be the same. This one says they're both going to be positive. Now, I never take this for granted. I always double check to make sure that I did this correctly. So I distribute. This gives me 16x squared. Cool. Then I get 12x plus 12x, which is 24x. Perfection. And 3 times 3 is 9. Done. Take a look at part E. We have 64x to the second power minus 80xy plus 25y squared. Okay. 64x squared. Definitely perfect. Perfect square, I should say. 25y squared. Another perfect square. Okay. Let's factor this. 64x squared breaks down into 8x times 8x. Notice your signs are going to be the same, but they're both negative. That's what this one tells us. Your signs are going to be the same. They both have to be negative. 25y squared breaks down into 5y times 5y. Always check. You never just want to write it down and move on because you never know. Always double check. 64x squared minus 40xy minus 40xy, that gives us negative 80xy, plus 25y squared. Check. Beautiful. Take a look at part F. When you explore factoring polynomials, again, as a reminder, first step is always GCF. We have 18x squared plus 48x plus 32. Do you see it? Do you see the GCF that's jumping out at you? Yes, you do. That's going to be a 2. So let's factor out 2 from all three terms and see what we get. 18x squared divided by 2, that leaves us with 9x squared. 48x divided by 2, that leaves us with 24x. 32 divided by 2, that leaves us with 16. Perfect. I'm going to go ahead and cover up the 2. Hold on to that. Notice I have a trinomial, and as a matter of fact, this is a perfect square, and so is our last term. We know that 3x times 3x gives us 9x squared. We know that 4 times 4 gives us 16. Okay, let's try it out then. Let's go ahead and factor this. Like I said, 9x squared breaks down into 3x times 3x. We know that our signs are the same, and they're both going to be positive. Let's break down 16. We see that's a perfect square, so it's 4 times 4. Double check. 9x squared plus 12x plus 12x, that gives us 24x, plus 16. Don't forget to bring that 2 down, and there is your final factored form. Awesome. Take a look at part G. So with part G, we have, okay, the first term is a perfect square. The third term is also a perfect square. We see that the first term is x times x, and this third term, when we factor, it becomes 4y times 4y, right? If it were a perfect square trinomial. Now, interestingly enough, let's just assume that I didn't even bother to really check the middle term. Let's say that I wrote, okay, well, x times x gives you x squared. And I know that the signs are the same. They're both going to be positive. And I know that 4y times 4y is 16y squared. If I distribute, I get x squared plus 4xy plus 4xy. Whoa, wait a second. That gives me 8xy, not 10xy. So what this means is that this is not a perfect square trinomial. If this were a perfect square trinomial, it would have to look like x squared plus 8xy plus 16y squared. That is a perfect square trinomial, but not this one. So you're probably thinking, well, does that mean it's not factorable? Well, let's test this out. We go back to our understanding of trial and error. So let's try trial and error. So we want to find factors of positive 16 that combine to give me a positive 10. So we have 1 times 16, that doesn't work. 2 times 8, oh, that does work. 2 times 8 is 16, 2 plus 8 is 10, so now we can actually factor this. So this becomes x plus 2y times x plus 8y. X squared plus 8xy plus 2xy, there's your 10xy, plus 16y squared. So it was actually okay that this was not a perfect square trinomial, because we can always fall back on the strategies that we've used before, which is trial and error or AC grouping, okay? Don't feel like you have to use one specific technique. Sometimes you have to kind of experiment and see what other things you can do, all right? Hopefully that made a lot of sense. And hopefully seeing this, you know, makes you think about the fact that all of these polynomials do not all fit the exact same mold. So you want to be really, really careful. Some polynomials you can only factor out a GCF and that's it. Others you end up having to factor multiple times, and that's okay. So I just want you to be super careful, super critical as you move through these factoring techniques, okay? Let's turn the page. Perfect. Now here is a brand spanking new concept, something that you definitely have not seen in 098. What this is offering to us is an opportunity to look at a 4-term polynomial and say, can I break this up 3 terms, 1 term? Meaning, can I say, is there anything we can do with the first 3 terms perhaps that is representative of any factoring technique I've already used? For this particular section in our notes, it's called perfect square trinomials in a 4-term polynomial. So there is no like secret there. We're going to end up seeing how a 4-term polynomial can have a perfect square embedded inside. So it's kind of an interesting and clever way of looking at polynomials. But let me show you. Let's take a look. So notice, let's fill in the top. Why not? So the general rule is you're going to look for 4 terms, right? 3 terms are, and I should actually say 3 terms represent a perfect square trinomial. Right? So 2 terms are positive perfect squares, 1 is negative. Isolate the negative perfect square, group the other 3 terms. They should factor into a binomial square. And then we're left with the difference of squares. So what you will want to end up doing here is use a U-substitution. So I'm going to make a note here. We will most likely use U-substitution. And I'll show you when. Not immediately, but I will show you when we use a U-substitution in this case. Okay. We have x squared minus 8x plus 16 minus y squared. Notice the first 3 terms. I'm actually going to highlight the first 3 terms. What I've just highlighted, x squared minus 8x plus 16, that's a perfect square trinomial. X squared breaks down into x times x. 16 breaks down into 4 times 4. Your signs are the same. They're both negative. So -4 and -4 definitely give us -8. Interesting. Okay, so let me factor this out. So just the first 3 terms, if I factor, becomes x minus 4 times x minus 4. Would you agree? Let's check. X squared minus 4x minus 4x gives us -8x plus 16. Cool. Then we have minus y squared. What we learned in this case is that we can actually rewrite this x minus 4 times x minus 4 as x minus 4 squared. Recall from our previous page, when we had an expression that was squared minus 36, we opted to use the U-substitution. We said, let's call x plus 5u so we can replace it and then factor using a familiar technique. We are going to do the same thing here. So we're going to call u x minus 4. So that means I have u squared minus y squared. Do you see it? Here we have the difference of 2 perfect squares. When I factor this as the difference of 2 perfect squares, that gives me u plus y times u minus y. U times u is u squared. Negative uy, positive uy, they cancel. Negative y squared. Perfect. As a reminder, because we used the U-substitution, We better put that right back. Wherever we see a u, we're going to replace it with x minus 4. So I get x minus 4 plus y times x minus 4 minus y. And that is the final answer. Not bad, right? So just to recap, when we have these 4-term polynomials, it may benefit you to explore seeing if there's a perfect square trinomial. You'll typically look at the first 3 terms and determine if that's a perfect square trinomial, and you'll rewrite it as the square of the binomial, the square of the binomial. Once we rewrite that in factored form as the square of the binomial, that's when we use a U-substitution. We say, let's call x minus 4 u in this case, replace it, so we have u squared minus u squared, and then we just go through the process of factoring the difference of 2 perfect squares. Okay? Let's do it again. Take a look at part B. We have x squared plus 6xy plus 9y squared, and then of course minus 49. Because I have my 4-term polynomial, and I'm noticing that my first 3 terms looks like a perfect square trinomial, I'm going to explore that path and see what happens. X times x gives us x squared. It's a perfect square. 3y times 3y gives us 9y squared. That's a perfect square. And we know that 3y plus 3y is 6y, right? Notice we have an x here, and we're going to actually get that x because of our first term. Let me prove that to you. This is, in fact, a perfect square trinomial. So x squared breaks down into x times x. Our signs are the same. They're both positive. 9y squared breaks down into 3y times 3y. Always double check. X times x is x squared. X times 3y is 3xy. 3y times x is 3xy. 3xy plus 3xy is 6xy. 3y times 3y is 9y squared. Perfect. And then, of course, we have minus 49. Let's rewrite this as x plus 3y quantity squared minus 49. Notice it makes total sense to use a U-substitution. U is going to be x plus 3y. So if I rewrite this as u squared minus 49, I can say, yep, this is definitely the difference of 2 perfect squares. So I'm going to factor it as such. So u squared breaks down into u and u. Negative 49 breaks down into positive 7 times negative 7. U squared minus 7u plus 7u, those cancel, minus 49. Awesome. And of course, because we made that substitution, you want to ensure that you place the x plus 3y back in each factor so that we're essentially putting this back in its original form. So u is x plus 3y. And then we have plus 7, of course. You never want to get rid of what's already there. And then again, u is x plus 3y. And we have minus 7. Beautiful. At this point, again, if you're watching this at a later date, pause the video. Pause the video, give yourself a shot for part C, and just see how comfortable you are with verifying you have a perfect square trinomial, rewriting it so it's a square of a binomial, using the U-substitution, factoring, and then plugging back in. You're probably thinking, there's so many steps, but I want you to see this as having a really logical flow. You know, it makes sense to be able to break this polynomial down in parts that are more manageable, right? You take this big ginormous thing and you break it down into more bite-sized pieces. And that's what we're doing here with these examples. Okay, so definitely pause the video at this point if you're watching at a later date, but everyone who's with me right now, let's check out C. Okay, same idea. We have 16x squared plus 72x plus 81 minus 144. Immediately, I'm noticing that the first three terms are definitely represent a perfect square trinomial. So I'm going to go ahead and factor this using the idea of perfect square trinomials. 16x squared breaks down into 4x times 4x. You know your signs are the same. They're both going to be positive. And 81 gets broken down into 9 times 9. Always double check. 16x squared plus 36x plus 36x, that gives us a 72x, plus 81. I love it. It works out. And then, of course, we have minus 144. We're going to rewrite this 4x plus 9 as the product of 4x plus 9 as 4x plus 9 squared. And then I'm going to use the U-substitution again. I'm going to say, let's call U 4x plus 9. Hopefully, as we continue to do this, it's starting to get, yes, James, that's so awesome. I was actually like hoping you would let me know what your thoughts were. I'm hoping that all of you are seeing, yes, this is actually making sense. This is useful in helping us to actually factor this completely. Why not use a U-substitution? It just makes life a heck of a lot easier. So 4x plus 9 becomes U, so U squared minus 144. I know that that's the difference of two perfect squares. We know that U squared breaks down into U and U. And then negative 144, that's a perfect square. We know 12 times 12 is 144. So we get plus 12 and then minus 12. As always, you don't just leave the U there, substitute that 4x plus 9 back in. So that leaves us with 4x plus 9 plus 12. And then 4x plus 9 minus 12. As always, if you see an expression like this, I hope that immediately you say to yourself, whoa, do not leave this like that. Make sure you go all the way by cleaning up, right? Simplify by combining like terms. So we have a positive 9 plus 12. That's going to give us a positive 21. So we have 4x plus 21. And then we have 4x. We have a positive 9 minus 12. That's going to give us minus 3. And there is your factored form. I would expect that at this point, you're starting to feel much more confident and you're starting to feel like, ooh, I'm getting all these skills under my belt. Keep in mind that factoring in this form, you're going to end up using again and again and again throughout the entire course. So consider the fact that you need to become masters of all of these techniques, okay? So practice makes perfect, but make sure you're practicing the correct format. Cool. Beautiful. Now we get into something again that is brand spanking new. When we were in 098 in elementary algebra, we described that if you were to factor a binomial, you would look for the difference of two squares. If you were in my class, I told you that there were more factoring formulas than that. There were two more specifically for binomials that we need to be accustomed to, and that is the sum or difference of two cubes. When we thought about perfect squares, we said 1 is a perfect square because 1 times 1. 4 is a perfect square because 2 times 2. 9 is a perfect square, 3 times 3, blah, 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 blah. But now we have to change our minds for a second and think perfect cube. 1's a perfect cube because 1 times 1 times 1, right? 8 is a perfect cube because 2 times 2 times 2. 27 is a perfect cube because 3 times 3 times 3, right? So we're getting very, very big very quickly. One of the ways that you can ensure if a numeric value is a perfect cube is by taking the cube root of it. I don't know if you're familiar with how to do that in the calculator, so I'm actually going to teach you because it's very helpful, especially if you're wondering, is this a perfect cube? Like, what's happening with this number right now? So let me show you what we can do with our calculator. So we already know how to take the square root of a number, right? So for instance, if I wanted to figure out whether 144 was a perfect square, I would say, well, let's take the square root. Notice I press second and then the x squared button. 144. And I see, okay, it's 12. So that means 12 times 12 is 144. Well, what about perfect cubes, right? So for instance, let's say I wanted to verify whether or not 64 was a perfect cube. Now, interestingly enough, notice this key here. It says the x root. Wow, that's hard to say. It's above your caret, which is the raised to the button. So it's above the caret in yellow because I have to press shift and then that button. So if I want the cube root, I'm going to say, let's take the cube root of 64. That's what that means. The cube root of 64. And that gives me 4. What that means is that if you take 4 and you raise it to the third power, you'll get 64, right? So for instance, we know that 5 to the third power, 5 times 5 times 5 is 125, which means if we saw 125 on our paper and we were wondering, is it a perfect cube, and we didn't remember, we're going to press 3, second, caret, 125, enter. Yes, it's a perfect cube because 5 times 5 times 5 is 125. That's going to be really, really helpful to you to think about as you progress through these problems. Okay, as with any of these, we have formulas. When we talked about the difference of two squares, a squared minus b squared, well, we know the factored form, a plus b times a minus b. Well, when we talk about the sum and difference of two cubes, it's a much lengthier formula. Nothing to be afraid of. It's just lengthier. No big deal. This is where index cards come in handy. Make sure on one side you write sum of two cubes, and then on the other side you have your formula. And just keep practicing until it becomes second nature, right? If you're at the dinner table, you're eating, and somebody else is doing the flashcards and just testing you, quizzing you, it's going to be super helpful. And heck, you might even have some fun. Okay. To prepare and to make sure that we understand how to use the formula, I've given you this example. So I'm telling you that a is equal to 3x and that b is equal to 5y squared. And all I want you to do is plug in these values in your expression. Our expression here is a plus b times a squared minus ab plus b squared. This happens to be the formula for the sum of two cubes. And you'll see that right below. But let's actually plug in and see how this goes. Okay, so we have a plus b times a squared minus ab plus b squared. Wherever I see an a, I'm going to replace it with 3x. So I have 3x plus, I'll leave a little gap. Then I have an a here and it's squared, so I'm just going to write 3x squared minus, I have an a here, and that's 3x. And I have another b here, so I'm just going to leave like an empty set of parentheses, and then plus, and we'll deal with the rest in a second. So everywhere I had an a, I replaced it with 3x. Now, everywhere I have a b, I'm going to replace it with 5y squared. Here's my first b. 5y squared. Here's my second b, 5y squared. Here's my last b, 5y squared. But remember, that b is squared. So I replace b with what its value is, but I don't forget that whatever b is, I've got to square it. So let me show you what that looks like. So our first factor, 3x plus 5y squared, doesn't change. There's nothing to evaluate. We don't have to worry about anything in there. Next, 3x squared. Well, 3x squared is the same as 3x times 3x. Well, 3x times 3x is 9x squared. So there's my first term. Then I have minus 3x times 5y squared gives us 15xy squared. 15xy squared plus. And then we have 5y squared squared. So let me do a little bit of side work. 5y squared squared implies 5y squared times 5y squared. Well, 5 times 5 is 25. Y squared times y squared is y to the fourth. So 25y to the fourth, close the parentheses, and voila, we are done with our substitution. So that is what it looks like when we make this substitution into the formula. We need this because when we break down our sum or difference of two cubes, we have to be so careful. We have to be super careful, especially here in this second set of parentheses, how we square that a, we take a times b, and then we square the b, right? We have to be super, super careful. I want you to notice in the formula, this is an a, this is just essentially like an a to the first power and a b to the first power. And then we have two a's here, we have an a and a b combo, and then two b's here. So think of it as like 1, 1, 2, 2, 2, right? And 1 and 2 make 3. I don't know if that made sense to you. My brain works that way. So when I saw it, I remember it's like, oh, 1, 1, and then 2, 2, 2. That makes sense to me because there should be a degree of 2 for each term moving forward. That's neither here nor there. Let me show you a different way of looking at this. So, how to factor a sum or difference of two cubes. Check it out. First things first, look for a binomial, right? It's got to be two terms. Both terms have to be perfect cubes. If this is going to work, they got to be perfect cubes. The signs used in the formula, meaning where you put the minus, where you put the plus, that kind of thing, follow this acronym SOAP. Same, opposite, always positive. Same, opposite, always positive. Okay, what the hell do I mean by that? If you have the difference of two cubes, your first sign is going to be the same, your second sign is going to be opposite, and your last sign is always positive. Isn't that kind of neat? Same, opposite, always positive. SOAP. Take a look at the second one, a cubed plus b cubed. The sign in your first set of parentheses is going to be the same, then opposite, and then always positive. Okay? Now in terms of what goes inside, just think 1, 1, 2, 2, 2. 1, 1, 2, 2, 2. Okay? A single a, a single b, then a squared, then ab, then b squared. It takes a little bit of practice. That's why I highly recommend using index cards to make sure that you solidify these formulas in your mind. You don't want to have to be looking up formulas every time you do these problems. That's going to be annoying. All right, let's actually factor using the sum or difference of two cubes. Part A, we have x cubed plus 27. This is definitely the sum of two cubes, right? The formula for the sum of two cubes is A plus B, same, right? Same, opposite, always positive. Okay? Same, opposite, always positive. 1, 1, 2, 2, 2. Sweet, 1 and 2 make 3. Cube, 3, right? Okay. X cubed, when we break this down, we know that becomes x times x times x. So when we break this down, it becomes x. Now keep in mind, I'm just writing x by itself because this is going to represent our A. The 27 breaks down into 3 times 3 times 3, right? 3 to the third power. What may be helpful to you is noting that whatever is in parentheses is going to be your A. Whatever's in your second parentheses is going to be your B. So A is x and B is 3. Do you see how I've rewritten this so that it looks like A cubed plus B cubed, right? Where A is x and B is 3. Now all we have to do is use these two pieces of information. So I'm actually going to highlight the x and the A and the 3 and the B, just so that I know, okay, everywhere I see an A, I'm going to replace it with an x. Let's start there. Everywhere I see an A, I'm going to replace it with an x. Don't forget that power. That's an x. Good. Everywhere I see a B, I'm going to replace it with a 3. Good. I see a B here, replace that with a 3. I see a B here, we're going to replace that with a 3. And now let's just clean this up. So my answer is x plus 3 times x squared minus x times 3 is just 3x. 3 squared is 9, and you're done. You cannot factor further. That's literally the end of it. Okay? And that is how you factor the sum of two cubes. The formula is going to be super helpful, and then rewriting it so that you break down each term into its cube root, right? So the cube root of x to the third is x. The cube root of 27 is 3. So you always want to break it down. Okay, let's take a look at part B. We have 8x to the third minus 125y to the sixth. Whoa, are these two cubes? Okay, let's think about this for a second. First off, I know that 2 times 2 times 2 is 8. And I know that x times x times x is x to the third. Okay, so this is definitely a perfect cube. It was 2x multiplied by itself 3 times. So that's going to be our A. Now, when we look at 125y to the sixth, hopefully we're not overwhelmed by that, but we know that 5 times 5 times 5 is 125. And we know that y to the second times y to the second times y to the second is y to the sixth. If you would like, please review your product rules for exponents. That way you are much more comfortable with that concept. I'm then going to highlight my A and my B. It's always going to be helpful. Take your time. Make sure you move through this slowly but efficiently. We know that this is the difference of two cubes. So difference of two cubes. It's the difference because it's minus, right? Simple enough. So the formula for the difference of two cubes, we've got same, opposite, always positive. Same, opposite, always positive. Good. We have already figured out what A and B are. A is 2x, B is 5y squared. Carefully substitute each of these. Now, as long as you're okay with this, and you can type into the chat, I'm not very comfortable with this at all, I'm actually going to replace it from left to right very carefully without just picking the A's and then just picking the B's. I'm going to replace from left to right. A is 2x minus B is 5y squared. Perfect. A is 2x, and we're squaring it. Plus, A is 2x, B is 5y squared. Plus, B is 5y squared, and I'm squaring it. Awesome. We substitute very, very carefully. We don't want to lose any powers as we move through this. With the first factor, the 2x minus 5y squared, that stays exactly as is. We can clean up the rest of this. When you take 2x and you square it, think 2x times 2x. That's going to give you 4x squared. When you see 2x times 5y squared, I want you to actually do the math. That gives you 10xy squared. So plus 10xy squared. And then plus 5y squared times itself, 5y squared times 5y squared is 25y to the fourth. And there is your final answer. Wonderful. Again, at this point, now that you have seen a few examples of plugging in and then actually factoring using the sum or difference of two cubes formula, this is another point where you may want to pause the video. Try part C on your own. Remember, the first step of factoring is always GCF. So if you're not seeing perfect cubes, it's quite possible that you have to factor something out first from both terms before you actually progress through the problem. So in this case, we see we have 54x to the 12th minus 16y to the 9th. Immediately, I know 16 is not a perfect cube, right? And 54 is definitely not a perfect cube either. But what should be jumping out at you is, hold on a second, I actually have a GCF. So I'm going to want to factor that GCF out first, so that I can actually progress through the problem. So immediately, I'm going to take out a common factor of 2. If I take 2 out of both terms, that leaves me with 27x to the 12th minus 8y to the 9th. Okay? Minus 8y to the 9th. I'm going to go ahead and cover up this 2. So I'm going to hold on to it, right? I'm not going to let it go. It's not going to distract me. And then I'm going to focus my attention on what's going on inside the set of parentheses. We have to say to ourselves, is this in fact the difference of two squares? This one's a little bit trickier because of such a large power. What I want you to consider is, if you were taking a cube root of a base with a power, you would essentially divide that number by 3, since it's the cube root. 3 divided by 3 is 1. 6 divided by 3 is 2, right? 12 divided by 3 is 4. 9 divided by 3 is 3. So that's another way to look at this as you break this down. So having said that, we know that 3x to the 4th multiplied by itself 3 times, 3x to the 4th times 3x to the 4th times 3x to the 4th, that's what gives us 27x to the 12th. So we have found our A. Minus, same thing here, what times itself gives you 8y to the 9th. Well, we know that 2 times 2 times 2 is 8. And we also know that y to the 3rd times y to the 3rd times y to the 3rd is actually y to the 9th. Okay, so remember, one way to think about this is just take that 9 divided by 3, right? Take that 12 divided by 3. That works with your powers, your variable base with a power. So I've identified my A and my B. I'm going to highlight these. A, B. Always do this. I promise it's going to make your life so much easier. Okay? Always do this. Also remember, I'm still holding on to the GCF. My finger's cramping. It's freaking cramping. Hold on to the GCF. Don't let it go. This represents the difference of two cubes. So we have A minus B. Same, opposite, always positive. Let's sub in. A is 3x to the fourth minus B is 2y to the third. And as we're doing this, we're moving really slowly and making sure that we are not losing track of anything. A is 3x to the fourth, and we got to square it. So 3x to the fourth, and we've got to square it. Plus, A is 3x to the fourth, B is 2y to the third. 3x to the fourth, 2y to the third. And then plus B, which is 2y to the third, and square it. I'm going to move that over just so that everything fits in the screen. Crazy, right? This problem's massive, but it's no big deal. We're going to clean up what's inside here, and then we're also not going to forget our GCF from the very beginning. I'm still holding on to it. So we have 3x to the fourth minus 2y to the third. 3x to the fourth times 3x to the fourth, so 3 times 3 is 9. X to the fourth times x to the fourth is x to the eighth, right? 4 plus 4 is 8. Product rule, keep the base, add the powers. Plus 3 times 2 is 6, and then we have x to the fourth and y to the third. Excellent. And then plus 2y to the third times 2y to the third, well, just think of it as 2 times 2, which is 4. And y to the third times y to the third is y to the sixth. I'm going to lift my finger up because I have my 2, which is my GCF, and I'm going to write it directly in front so that there represents the final answer. Doesn't it seem a little bit crazy? There's a lot going on in here, but it really is all about moving slowly through the problem, not losing any of those powers that you see, and I'm going to show you this again, not losing any of the powers that you see within the set of parentheses, and just applying everything very carefully. You don't want to lose track of any of your rules either. Okay? We have one more to try that I think would be really awesome to see. And that is part D. We have x minus 2 to the third power plus 64. I'm hoping that when you see a problem like this, that right away your mind says, U-substitution, right? We want to represent this as something that we are familiar with, as something that we're used to. So we are going to call U x minus 2. Do you see the application? I think at this point you're a freaking pro. I think at this point you're like, okay, I totally understand why I would be using this U substitution. So that leaves us with U to the third plus 64. We're going to go ahead and note that U times U times U gives us U to the third. And that 4 times 4 times 4 gives us 64. So I just found my A and my B. Let's go ahead, highlight these. Man, this highlighter, it's really helpful. I'm telling you, get a highlighter, make your lives easier, okay? Sometimes it really helps to see things kind of lit up like this, right? We're going to go ahead and write the formula. At this point, I feel like the formula is embedded in your brain. And if it's not, that's okay. Just keep practicing. You're going to find that it will be. So here we have the sum of two cubes. So same, opposite, always positive. Cool. Everywhere we see an A, we're going to replace it with a U. Everywhere we see a B, we're going to replace it with a 4. So that gives us U squared minus, and if this is U and this is a 4, U times 4 is 4U. I hope you don't mind me just cleaning that up immediately. And then B is 4, and 4 squared, 4 times 4 is 16. Again, I hope you don't mind me just going into the simplified version of this. Now, as we know, that x minus 2, what we replaced with a u, what we substituted with the u's, gotta go back. So we have x minus 2 plus 4. Now here's a kind of pain in the butt situation. Don't think too much into it. It's not a big deal. It's just a little bit of a lengthier process. U is x minus 2, but it's being squared. Then we have minus 4 times x minus 2, and then plus 16. So x minus 2 plus 4, we can clean that up, no big deal. So that gives us x plus 2. Now inside this set of parentheses is going to end up being a little bit of a pain in the butt. So let's do some side work. We have x minus 2 squared. You're probably thinking, can I use a U-substitution again? Please don't do that. Because we're not factoring. We're just opening this up. We're expanding this. So x minus 2 squared is the same as x minus 2 times x minus 2. So I'm going to do a little bit of side work so that I don't clutter up this entire space. So this gives me x squared minus 2x minus 2x plus 4. Right? When I clean up my like terms, I get x squared minus 4x plus 4. So now I can put that right back here. I always like to do side work so that we don't clutter up our space and then lose all sorts of information. It just makes it so much easier when you're organized. So x minus 2 quantity squared is x squared minus 4x plus 4. We're going to distribute the negative 4 throughout the second set of parentheses, right, within this set. So we have negative 4x plus 8 plus 16. And all that's left is to combine like terms. So we have x plus 2 times, we have x squared as our largest term. I have a negative 4x and another negative 4x. These are like terms. This is going to give me negative 8x. And then I have 4 plus 8 plus 16. So if I have 4 plus 8 plus 16, that's going to end up giving me 28. So plus 28. And there is your final answer. All right. At this point, I'm going to end here. That was essentially a 2-hour class condensed to an hour and a half. Because obviously we don't build in time to work through problems. I hope that this video was incredibly helpful. I hope that all of those factoring techniques are just like starting to sink in and you're starting to be a little bit more comfortable and confident with those things. And as always, just keep practicing, okay? Make sure you get those index cards, write the formula on one side, write the name on the other, and just flashcard, you know, just test it out. Quiz yourself, see how that goes, and apply those to your problems, the ones that you practice. The next section in our notes has an overview, so a general procedure for factoring a polynomial. That's essentially pages 14 and 15. I would urge you to, once you are all done with understanding these techniques, these factoring techniques, I would urge you to try those problems, because that's essentially saying, hey, can you collect all these ideas and put them together? If I don't tell you which formula to use, do you know what you're supposed to be using? So over the weekend, try the problems that are under the general procedure for factoring a polynomial. That is pages 14 and 15. Give those a shot, see how you do, and in Monday's class, we're going to breeze through those and make sure that you did them correctly. All right? Good luck, everyone. Don't forget to check in with each other, circle in. Jeff's available. Please make sure you're working with a partner, a buddy, and can you continue to do fantastic work. Bye, everyone.